Good evening. So, welcome to today's class. Um, I don't know, I think it's a Saturday and everybody's out having fun. I think it will just be you and me, Krishna. And yeah, Anamta is also joined. So, in the last class, we discussed, we had discussed about the connection of transpiration, assimilation, stomatal conductance, and its how it is affected by relative humidity and concentration of carbon dioxide in the atmosphere. And we did some problems so that you guys can have an understanding of the uh, estimations of transpiration and assimilation and stomatal conductance, and what is the difference between stomatal conductance in of water to stomatal conductance of carbon dioxide, how they are different, and what is diffusivity and how it gives a relation between the two. Then we also did some problems to read the psychrometric chart to find out the quantity which is available to us through. Generally, weather data available to us can be projected to quantities that is required when we need to model plant. So those problems will definitely help you in having an understanding as to how you can make use of these data when you need to apply it on in terms of plant physiology, modeling of plants basically, and modeling these processes more importantly. So today we'll be looking at this model called the Bolberry model. So yesterday we looked at a very simplistic representation of assimilation and transpiration. Assimilation is related to the stomatal conductance to carbon dioxide and the concentration gradient between the atmosphere and the leaf, and the transpiration is related to the stomatal conductance and the vapor pressure deficit. Now there are various models that have been also been developed to give a more robust association of stomatal conductance to the environmental variables and photosynthetic rate, and one such model is the Bolberry model. So in the Bolberry model, it is giving a direct relationship between stomatal conductance and photosynthetic rate, as well as the environmental variables like relative humidity and carbon dioxide concentration. So a bit different from what we had looked at yesterday. We have one particular equation for assimilation, one particular equation for transpiration, and transpiration is associated with humidity quantity, assimilation is associated with the carbon dioxide quantity. So here what we are getting is we are getting the stomatal conductance as a function of or as dependent on photosynthesis, humidity, and carbon dioxide concentration. So all of that is combined into one entity called the Bolberry index, and then stomatal conductance will be connected to this Bolberry index through this model. So this is basically again giving us an idea how the stomata is going to open and close in response to carbon dioxide uptake and water loss through transpiration. And the model is nothing but a line that is a linear regression model that has been developed with the slope quantity, the dependent variable, the independent variable being this Bolberry index. You see here An into Hs by Cs is the Bolberry index, and then B naught as the intercept value. So this is nothing but an equation of the line in the format y is equal to mx plus c. So you can see here it is y is equal to mx plus c quantity, mx plus c. Here y is the stomatal conductance, m is this, sorry, this B1 term, c is this term, and the quantity x is this term. So this is how are we arriving at this line, and how what are these data points over here is what we look into more in more detail. Yeah. So here, as you can see in this equation, this Ball-Berry index is the product of the net photosynthetic rate or net assimilation rate into HS, which is the relative humidity at the surface of the leaf. It is not the relative humidity that you get measured directly from the weather data. It is the relative humidity at the surface of the leaf and the carbon dioxide concentration at the surface of the leaf. So when you see, in a field condition or an actual condition, when you look at a plant, the plant will be experiencing humidities at varying levels. Now, if you see the top leaves will be more exposed to the air as compared to leaves which are going to be somewhere in the middle of the canopy. So this is called canopy microclimate and it varies. So what we are focused on is what exactly is the relative humidity just above the surface of the leaf and not on all the layers that is very much above to the leaf. So the data we usually get from weather stations are the relative humidity data. So that data we will have to convert to the relative humidity at the surface of the leaf and multiply it with the net assimilation rate and divide it by the carbon dioxide concentration also near the surface of the leaf. So if we have the atmospheric carbon dioxide concentration, we will be able to find the concentration of the carbon at the surface of the leaf. So this term, the Ball-Berry index, is a product of AN into relative humidity at the surface of the leaf divided by the carbon dioxide concentration at the surface of the leaf. Now, suppose we are taking this Leica 6800 instrument that I had explained to you in the earlier classes and we are getting measurements of stomatal conductance and photosynthesis. From that, we will calculate this term AN into HS by CS and we will plot it in a graph like this. So you can see here, these black dots in this graph are indicating the measurements that were done on day 1. Then the white dots are the measurements that was done in day 2 and the triangular ones are the measurements that were done on day 3. And then we'll plot it we'll make a scatter plot out of this with the x-axis as this Ball-Berry index and y-axis as the stomatal conductance. So we'll get a scatter plot like this. And what we'll do is we'll do the least squares method. We'll apply the least square method or the linear regression model for each data set, day 1, day 2, and day 3. And we will find out the equation of the line that best fits these points. So the equation of the line is the line which will best represent the relation between the y-axis and the x-axis. That is what the linear regression model does. So the linear regression model here, what we are getting is the best fit line that is going to describe the relationship of the stomatal conductance with the Ball index or the Ball-Berry index. So in this equation, if you look at this term, which is a slope term, B1 is the giving us the sensitivity of the stomatal conductance to photosynthesis, and B0, which is the intercept, is giving the baseline conductance when photosynthesis is negligible. So next, let's look into what are each of these terms. So like I said, the Ball-Berry curve is a linear regression model giving us the relationship, the best fit relationship between the y-axis, which is the stomatal conductance, and x-axis, which is the Ball-Berry index. Now, a linear regression model, it is a statistical method. It is describing the relationship between one independent variable, which is the x-axis, and one dependent variable using a straight line equation. So we know a straight line equation. We are familiar with straight line equations in this format. We know straight line equations as y is equal to mx plus c. So here again y, b0 will the intercept, b1 will be the slope, x is the independent variable, and or epsilon is the error term that is account for the random variation occurring in all of these points. So in order to find the slope and the intercept, what will we do? Or how will we find this best fit line is what we look into now. So in this, from this graph, if you look at it, we have the slope term, we have the intercept term. So in order to find the slope and intercept, only if we find the slope and intercept can we find the equation of the line that is best fitting these points to the independent and the dependent variable. So slope can be found out with this equation. This is the linear least square method that we have all, I think, learned at some point. I don't know. In school, we have learned all of this, but again, just to refresh your memories, the linear regression model is nothing but finding the slope and the intercept from a bunch of x and y axis points. By first, what you'll do is you'll find the average of the x points. That is, x-axis here is an into hs by cs. So this average value of this, all the data points in this x-axis will be found out. Average of the stomatal conductance terms will be found out. And after that, you will find out xi minus x bar and into yi minus y bar. Xi is nothing but it is each point. So if you have 5 x-axis value, the first value minus the mean into the first value of the y-axis minus the mean of y-axis. And for each point, suppose you have 5 points, for the 5 x and y values, you will find this relation and you will get the sum of it and then divide it by the square of the xi minus x bar, the whole square. The square, you'll square this value that you're getting for each point and then you'll take a sum of it, and this numerator you will divide it by the denominator. Similarly, in the y-axis, what we'll do is we have already got the slope value. So we will subtract the mean of the y-axis minus slope into mean of the x-axis, and you will get a slope equation. Now, from the slope equation, we can find out the relation of this line equation. That is, the equation of the line will be a into x plus b, where a we will find out from this one and b we will find out from this one. So this is how you will get the each of these lines you see here. These lines have been obtained from by solving the points of x and y axis. X axis is this one and y axis is this one. So by solving for the number of points, here you see a lot of black points. For each black point is representing one coordinate of x and y axis. So for using that each point, we are going to make use of this equation a and b, find out the slope and intercept, and find out the line equation. So this is a linear regression model that is being used. And just to, so that all of you can be familiar with how this estimation is done, I'll be giving a problem now. Kindly do it with the help of Excel, because if you sit to do it manually, it will take a lot of time. You can attempt it, but I would suggest using Excel or some scientific calculator where you can do the calculations fast. So here I have given a set of values of photosynthetic rate and stomatal conductance rate. You don't have to worry about the HS and the CS term, which is 1. So basically the x-axis is giving the value of the photosynthetic rate of the Bolbury equation. What I want you to do right now is, for each of this point, find what is xi minus x bar, yi minus y bar, multiply it, the sum, and then divide it by the sum of the squares of this x term. So please make use of Excel and do this problem. I hope all of you have access to Excel. And I mean, those of you who don't have it, it might take a lot of time. So if you have Excel, please kindly do that. And if you don't have, please put a message in the chat room so that we can go ahead with the solution if no one is intending on doing it. So please to respond to that. I think it will be good for you to know this, because later on when you want to create a Bolbury, say suppose you want to create a code or you want to make an Excel sheet that will give us the Bolbury curves for a particular bunch of data, then how to do this will help you. So please do attempt it using Excel sheets. And if you don't have Excel sheets, just drop in a message in the chat, so that if none of you are attempting, I think I'll just go ahead. Is anyone trying to do the problem? Okay, so I'll wait. First, enter these values into an Excel sheet. One for x-axis, one for y-axis. You know which is y-axis, you know which is x-axis. Then find the mean of all those values find the mean of this photosynthetic rate, find the mean of stomatal conductance. After that, for each point, find x minus x bar and y minus y bar. Multiply it and find the sum. So when you're done, just drop in a message and I'll give you the solution. Yeah, you're almost done. Okay, I think I'll move on to the solution. Harita, are you done? Can I go ahead? Okay. So, how many of you had a subject in your 11th and 12th, this maths? You can raise hands here. Okay. Slope and next the intercept value. Let's see if the answer is correct. So when you do it in Excel like this, we have the x-axis as 5, 10, 15, 20, and 25. We'll find the average of this, which is equal to 15. I think more than this, it's better to share the Excel sheet. So I'll just share the Excel sheet. Share. If you see here, we see that these are the x-axis point 5, 10, 15, 20, 25, and these are the y-axis point 0.1, 0.2, 0.25, 0.3, and 0.35. So first what we'll do is we'll find the average of this. Average, we can either add all of this and divide it by 5, or there is a um, formula in this one where you type average and you can do find the average of the cell. So you'll get 15 over here. So x bar will be 15. This is equal to x bar. This value is going to be x bar, this thing that you see here in this equation. You see x bar over here, that is the average of it. Now next, we are going to do the same thing for y also. In order to find y bar, we'll press equal to average and then average of all these 5 cells, and we get it as 0.24, which is y bar. Now what we have to do is we have to find what is x minus x bar for each of this point. So this is x. So 5 minus 5, the average is 15. So for all of these value, the x bar is going to be 15. Only value that is going to be varying is the x value. So here it will be 5 minus 15, which is minus 10, 5 minus 10, which is minus 5, 10 minus 15, which is minus 5. That 15 minus 15, 0, 20 minus 15, 5, 25 minus 15, 10. In the same way, we will find what is y minus y bar, which is 0.1 minus 0.24, 0.2 minus 0.24, 0.25 minus 0.24, 0.3 minus 0.24, and 0.35 minus 0.24. So this is how you find x minus x bar and y minus y bar. I think one of you, the mistake that you've done is you have found out this x minus x bar, the slope for each of the points, which is not necessary. The slope value and the intercept value will be just one value for one line. So, but we are getting that one line from a number of points. Now, after finding x minus x bar and y minus y bar, we will multiply the two. That is, you will multiply this value into this value and you'll get x minus x bar into y minus y bar value. Here also you will do it for the second point, third point, fourth point, and fifth point. Now next, what we have to do is for the numerator, we have to find the sum of all of these values. That is, if you see the formula in here, the numerator is the sum of, this sign is the summation symbol. So summation of the product of these two values. So summation of these two values will be the sum of this column. So here we will get the final answer. The numerator as value will be 3. Now for the denominator, b is x minus x bar the whole square. We have to square this column. Now we found out what is x minus x bar. So here we'll create a column which is the square of this value. So x minus x bar the whole square, which is 10 square, 5 square, 0, 5 square, 10 square. So we are getting 250 as the sum of all of these values in the x minus x bar the whole square. So that will be the denominator value. You find here the denominator over here is the summation of all of the x minus x bar the whole square. Now we got the numerator and denominator. If we divide the numerator by the denominator, we will get 0.012, which is basically the value of the slope. So slope is equal to xi minus x bar into yi minus y bar, sum of all of it divided by the sum of x minus x bar the whole square. So the slope we get is 0.012. Now we know 15 is the intercept, 15 is the average of the x value, and 0.24 is the average of the y value. So intercept can be found out by subtracting the average of y minus slope into x bar. So that value will be this. We are actually 15 doing 15 minus slope is 0.012 into 0. Sorry, it's y minus. So equal to 0.24 minus 0.012 into 50, which is 0.06. So we got the intercept value as 0.06. So our line equation will be equal to, this. That is y is equal to y is equal to slope is 0.013. So 0.012x plus intercept is 0.06. 0.06. So if you see the graph over here, this is the line equation. So the equation of this line is 0.012x plus 0.06. So this is how the linear regression model works. But it is good you attempted, so you understand where you might be going wrong. So for one line, we'll have one slope and one intercept. Now in Excel itself, what you can do is, if you plot these points, now I'm plotting this as a graph over here. This, say a new graph I'll plot here. Insert, chart, XY scatter. I get a scatter like this. And then when I right click or chart tools, add element, there is an option called trend line. So if you add this linear trend line, you will get this this is making use of this linear regression model. This is all the calculations that are going inside to get this linear regression model. And here, when you go to formatting this option, you can select display equation on chart and you will get the slope and intercept value. So here we have got, this is the slope and intercept value. 0.012 is again the slope that we calculated. 0.06 is the intercept that we calculated. So this is how we do the estimations for a linear regression model. In Excel and when you're coding, there are already codes available for a linear model. So we don't have to do all these calculations, but then it is good to know how what is the small estimations within this model for getting the final equation of the line. So this is how it is done. So we understand that the Ball-Berry model is nothing but a line that is representing the relationship between the y-axis and the x-axis. Now the slope value is actually giving us the difference. That is, slope in general is the difference in the y value to the difference in the x-axis value. So here, for a set of points that I've created, we know that these are the x-axis value, these are the y-axis value. Suppose you take 2 points, 8 and 5, then 8 minus 5 by the corresponding x value is 5 and 3. So 5 minus 3 will give you as 1.5, the slope value. So the slope is found out if we know what is the value of the x and y, accurate values of the x and y. This is basically how the slope is slope represents. And the intercept is nothing but say suppose this point is not there. If you can see here in this graph, the line is only till here. So if you choose to extend this line beyond this point over here, you choose to extend this point beyond this line over here, you will see that at axis of 0, when the x value is 0, this y value will be equal to 0.6. So this is what the intercept of the point usually represents. So this is nothing but one is giving us the difference in the delta y minus delta y by delta x, and intercept value is nothing but at 0 x-axis, what is the value of the y-axis? Where is the y-axis intersecting the line equation is giving us the intercept value. So same way, when we use this interpretation for the Bolberry, the intercept value is nothing but it is the baseline conductance. We know that from this graph, we know that GS is the y-axis value and Bolberry index is the x-axis value. So from this we can know that the y-axis value when this x-axis is 0, that means when photosynthesis is 0. Now relative humidity and carbon dioxide concentration is not going to be 0. So in that case, this x-axis will be 0 only if the photosynthetic rate is 0. So when the photosynthesis is 0, what will be the stomatal conductance is the interpretation of the intercept value in this equation. So the intercept in this is giving us the baseline conductance when photosynthesis is negligible or photosynthesis is 0. So when photosynthesis is 0, there will be some amount of stomatal conductance, that too to water vapor. So here the stomatal conductance is always the stomatal conductance to water vapor. It is not the stomatal conductance to carbon dioxide. So Bolberry is giving the stomatal conductance to the Bolberry index, the conductance to water and not to carbon dioxide. So what we are understanding is even when the photosynthesis is 0, the stomata will be open and some amount of water will always be going out. And depending upon the value of that intercept, it will be high or it will be low. So if the so if you see here, if for this line which is having a higher intercept and for this line which is having a lower intercept, we can see that the stomatal conductance when the photosynthesis is 0 is 0.4 and stomatal conductance when photosynthesis is 0 is 0.2. So this line will basically have more stomatal conductance even when photosynthesis is not taking place than this line. So this is going to lose more water in comparison to this line. And this line can be anything. It can be a plant or it can be another leaf of a plant or it can be another species or it can represent the measurements like the data that we had seen earlier, measurements at a different time. So it can represent anything. Okay. So that is what the intercept is the value of the what does the intercept mean? Now in this Bolberry equation, this ball index that you see, AN into HS by CS, let us go more deeper into the unit of that. Now this is the ball index, that is AN into HS by CS. Now we know that assimilation rate is always represented as the micromoles per meter square per second. So that is the value over here. HS is relative humidity. Relative humidity does not have any it is basically a percentage value. So it is dimensionless. So we are not using any unit over here. And carbon dioxide concentration is in micromoles per mole. So when these two terms cancel and this mole goes to the numerator, we'll get the unit of mole per meter square per second. So the Bolberry index's unit is also mole per meter square per second. Y-axis value is also in moles per meter square per second. Now, when I say that the intercept is larger or intercept is lower, it means that for when is usually the photosynthesis very negligible. In case of a C3 plants, during night time, the photosynthesis is going to be very negligible. So during that time, what is the stomatal conductance is what is being given by the this intercept value of the Bolberry curve. So if this red line is giving us a plant, a particular plant, and green line is giving another plant, we can say that plant one is losing more water than plant two. So this is again giving us information about the water use efficiency, how efficiently a particular plant is making use of water. And in this case, plant one is losing more water because of this leakage due to this minimal stomatal conductance that is still lasting even when photosynthesis is not existing. Now, what does the slope give? What information does this slope give? So here, if you see, we know that at say suppose this value is constant, HS by CS is equal to 1, and AN is the only value that is varying, then at a value of 5 micromoles per meter square per second, this line is having lesser stomatal conductance than this line. So slope is actually for this line, the slope is higher because, and as the slope becomes more steeper, the stomatal conductance value increases, and as the slope reduces, the stomatal conductance value reduces. So in this case, you are seeing that the brown line has a lesser slope value than the blue line, which is indicated that for the same photosynthetic rate, the stomatal conductance is higher for blue line than brown line, which is saying that stomatal conductance is more sensitive to photosynthesis in the case of the blue line than the brown line. So again, blue can be some plant or some another leaf or some other day's measurement, and brown can be representing another plant or species or whatever. But what the slope value gives us is the sensitivity of the stomatal conductance to photosynthetic rate. So here in the Bolberry equation, this value, sorry, this is B1. This is not. This is B1 and this is B0. Okay, so the slope is giving the sensitivity of stomatal conductance to photosynthesis, and the intercept is giving us the baseline conductance, or the stomatal conductance when the photosynthesis is negligible or when photosynthesis is not existing. Okay, so when I specifically stressed on the relative humidity and the carbon dioxide concentration that we are taking. The relative humidity is not the atmospheric relative humidity we are having. It is the relative humidity here at the surface of the leaf. Same in the case of carbon dioxide concentration also. It is on the surface of the leaf. So basically when we have to measure the stomatal conductance, which is the rate with which this carbon dioxide is entering this, water vapor is entering the stomata, we also have to estimate what is the conductance or resistance that is offered to this water vapor. Sorry, carbon dioxide and water vapor. Suppose water vapor is going out over here, the total conductance is the total conductance, not the stomatal conductance. The total conductance will be the sum of the stomatal conductance, which is the conductance from the inside of the leaf to just the surface of the leaf, and from the surface of the leaf to the air part. So this is what the total conductance will be. Till now we were looking at the stomatal conductance, but the total conductance will include what is the conductance of water from the inside of the leaf to the surface of the leaf, and from the surface also, if it has to go more above, there is a boundary layer that is existing through which the wind and all will play an important role, which will affect the movement of the water vapor to above. So total conductance will be the boundary layer conductance along with the stomatal conductance. Now, is it a sum of both of that? We'll look into it right now. Same is the case of carbon dioxide concentration. When carbon dioxide is entering the stomata, it has to cross this boundary layer, reach the surface of the leaf, and then go inside. So, total conductance of stomata or stomatal conductance to carbon dioxide will be the boundary layer conductance along with the stomatal layer conductance to carbon dioxide. Now, we have all learned about resistance, series connection, and parallel connection. So, this is also something related to that. I don't know why. Okay, this is also something just similar to that. We'll have a bit of physics in here now. Okay. So here what we see is when we had learned about resistances, we see that resistance in a series connection is total resistance is found out as a sum of the two resistance. And in parallel connection, it is found out like this 1 by R1 plus 1 by R2. This is this is the basic theory that is used wherever there is series and parallel connection. Even when it comes to in soil, if anyone of you are familiar with soil study, soil layers are stratified. So if the layers are in parallel layers, then how will the water move? Will be if it is in parallel way, the conductance or hydraulic conductivity is measured, is represented like this, and if it is in horizontal way in a series way, then it is represented like this. So in series connection, it is always the sum of the two resistance, and in parallel connection, it will be in this form. The same way, conductance is also like this, except that if resistance is the sum over here, conductance in a series connection will be in this format 1 by 1 by G1 plus 1 by G2, because the reciprocal of the resistance is the conductance. In in evapotranspiration and all, the Penman-Monteith equation is making use of the surface resistance term. So when we are representing resistance, we can represent it as a resistance, but when you're converting it into conductance, you have to take the reciprocal of that value. So in the case of conductance, for a series connection, the total conductance will be 1 by G1 plus 1 by G2, and in parallel connection, it will be G1 plus G2. So in here, what we are having is it a series or a parallel connection? You can see that the resistance are going like this. Series means one after the other. Parallel means one above the other. So what is the conductance? How is the conductance over here connected? Is it a series connection or a parallel connection? Drop in your answers in the chat box, please. You can see from the diagram here, the red line and the brown line. Yes, that's right. It's series connection. So let's go back. Yes, right. It is series connection. So if you go back here, series connection, we see that the total conductance is 1 by G1 plus 1 by G2. Correct. All of you are right only. Manish, Mayank, Harita, Ryan. 1 by G1 plus 1 by G2. So in our case also, we can do the same calculation for the uh, boundary layer conductance and the stomatal conductance. So in that case, if GSW is the stomatal conductance of vapor through leaf, that is whatever vapor is going out from here, from the inside of the stomata to the leaf surface, that is the stomatal conductance to vapor over the leaf, and boundary layer conductance is given by GBW, then the total conductance will be this value. This is how I obtain this is nothing but 1 by GSW plus 1 by GBW. Now, when you GBW plus GSW divided by GSW into GBW. And if you take this to the numerator, it will come in this format. So this is how I got that equation. So the total conductance, which is to water vapor, which is the boundary layer conductance as well as the conductance of the water vapor from the surface into the leaf or the leaf into the surface, is given by this equation because it is in a series connection. So what happens to the conductance of the carbon dioxide? You see that total conductance will again be conductance of the uh, stomatal conductance to carbon dioxide over the surface, and the total boundary layer conductance to carbon dioxide divided by sum of the stomatal conductance and the boundary layer conductance. But we know that the stomatal conductance to carbon dioxide is stomatal conductance to water vapor divided by 1.6, considering the diffusivity coefficient that we had studied in the last class. Water is a more smaller molecule, so GSC, I mean the carbon dioxide will be diffusing at a more slower rate, which is again represented by the diffusivity coefficient. So you have to divide the water stomatal conductance by 1.6. In the same way, boundary layer conductance also has to be divided by 1.37. Now here it is 1.37 because in this layer only the molecular diffusion is being considered. But when you go upper and upper into upper layers, which is mostly the boundary layer, there will be some eddy diffusions and turbulent activities also. So those forces also have to be taken into consideration. And after all of that, the diffusivity coefficient that we are getting is 1.37. So same like how we are dividing the stomatal conductance to water vapor with 1.6, we will divide the boundary layer conductance by 1.37. And then we will substitute this in this equation and we will get the GTC is equal to this in this format, GSW into GBW by 1.6. This is how you will get it in terms of the water's conductance. Now, why we need all of this is when we are estimating the surface of the carbon dioxide concentration on the surface, we need to know the boundary layer conductance to carbon dioxide also. So this is the way the Likert instrument, this I just wrote this equation here too, so that you can understand how the Likert instrument is estimating the internal carbon dioxide concentration. In the same way, it also estimates the carbon dioxide concentration on the surface of the leaf, and it is a function of this boundary layer conductance to carbon dioxide minus the rate of the transpiration into the ambient carbon dioxide concentration minus the net assimilation rate. So if the instrument needs to find the carbon dioxide concentration at the surface, it needs to know the boundary layer conductance to carbon dioxide also. And to know that, we should know the boundary layer conductance to water, which is then converted to boundary layer conductance to carbon dioxide and used in this equation to find the carbon dioxide concentration on the surface. So one part of the equation we found out. We have the AN, suppose we have the measurements for AN, we can estimate carbon dioxide concentration CS in just the way I told now. HS is nothing but the vapor pressure at the leaf surface to the saturated vapor pressure inside the leaf. Now, one change from what we learned in the last class is that this humidity is represented as the ratio of the partial pressures of water vapor on the surface of the leaf and in the interior of the leaf, not the mole fraction. So if we want to know the HS value, we should get the partial pressures of water vapor in air and partial pressure of vapor inside the leaf. And then in order to get the saturated vapor pressure inside leaf, this is represented as a function of the leaf temperature. And so we can estimate, if we know the temperature of the leaf, we can estimate this value. And on the surface of the leaf, if we know from the psychrometric chart in that gives us the values of partial pressures, we can obtain the relative humidity at the surface of the leaf. And then by dividing these two terms, we'll get the relative humidity at the surface of the leaf. So all these estimations, when we are talking about the Bolberry index, which is just a simple line equation, all these internal estimations are done. And all these estimations have been incorporated into the Ballberry model in BioCro software, where if we give the relative humidity value, the temperature of the leaf, the temperature of the air, the ambient carbon dioxide concentration, all of these values will be estimated and we will get the Ballberry curve generated by the model. Now, I explained what is the relationship, what is the intercept value and what does the stomatal conductance value represent in a Ballberry equation. So in this question, there are three lines in this graph representing one line representing one plant, or say it is one plant. Out of these three plants, which plant has the highest baseline stomatal conductance when photosynthesis is zero, and why? Please put in your answers in the chat box. You can direct message me. By I have given the line equation also, and I have also the graph is also here. This is the Ballberry equation for one plant. So out of this, which plant has the highest baseline stomatal conductance when photosynthesis is zero? Just observing the graph and pretty simple exercise. You've got some answers. No more answers? I just got two answers. So the intercept value gives us the baseline conductance, slope value gives us the sensitivity towards photosynthesis. So which has the highest baseline stomatal conductance? Only two answers. Please give me some more answers. Okay, nobody seems to be interested. So let's move on to the line 3. Yes. So all of you are right. It is this red line which has got the highest baseline stomatal conductance. And because the value is 0.07 out of the three lines, it is 0.07 which has the highest value. So what does this mean is that this is keeping the stomata slightly open even when the photosynthesis is not happening, and this is mainly to keep the transpiration process going on. And like I said, transpiration is not just water loss, it will help in the cooling of the plant also. So probably because of that requirement, the stomatal conductance value is in, and when the photosynthesis is zero, is such. Now, in this, from this graph, which plant's stomata responds more rapidly to increasing photosynthesis? Yes, Ryan, your answer is right. Harita's answer is wrong. Anybody else? Yeah, now your answer is right. No, Manish, it's not the and no. Okay, so most of you gave the right answer. So why is it the correct answer is the red line? Why do you think it is the red line? You don't have to look at the graphs or anything. You just have to look at the line equation over here. The slope value is highest for this red line, which is 0.015. So slope is giving the sensitivity of stomatal conductance to photosynthesis. So as photosynthesis increases, stomatal conductance, tendency of stomatal conductance to also increase is more for the red line as compared to the other two lines, because that can be obtained from the uh, slope value. So if you see for between 15 and 20 values of photosynthesis, if you see here, if you see here, this is 15 and this is 20. The slope value, which is actually a difference of point say 35 and 0.25, will be lesser in the case of this line. For same this one, you will see the difference is less. It is 0.25 minus zero point 0.2 over here, whereas here it is 0.35 minus 0.25. So that is why we are saying that the from the slope value, if the slope is a higher value, it means that it slope is higher means the line will keep going like this. If the slope is lower, the line will keep it will go more closer to the x-axis. So since the slope is high in the case of the red line, we can say that the red line or this plant that is corresponding to red line has the highest sensitivity to stomatal conductance. Now, which plant has the lowest water loss at low photosynthesis but opens the stomata aggressively as photosynthesis increases? Okay, let's look at the answer. Yeah. So again, the red line, because from the intercept value, we know that red line has got the least least intercept, which means the least baseline conductance. So water loss is the least for the red line, but then the slope is the highest for the red line, which is saying that as the photosynthesis increases, the stomatal conductance sensitivity will keep increasing. It is more sensitive, so it will keep increasing more and at a faster rate when compared to these two other plants. And this is probably because it is a drought resistant plant. That is the physiological interpretation we can make. So this plant is not losing much water, but again it is very photosynthetically efficient. So if there's a lot of light and carbon dioxide, nice photosynthesis also will take place, but again water loss is less, which is saying that okay, this plant is a drought resistant or drought tolerant plant. So these are the physiological interpretations we can make from these curves. We can decide if the plant is water use efficient or drought resistant, or whether it will lose more water or it will save more water, or whether it is photosynthetic rate, which is if you compare the lines of different plants, we can know that This one stomatal conductivity is more sensitive to photosynthesis. So because of that photosynthesis, as the photosynthesis increases, stomatal conductance also keeps increasing. And this gives a lot of physiological information regarding the transpiration rate, water use efficiency of the plant. Now, hypothetically, if the environment is suddenly being drier, which plant is likely to reduce its stomatal conductance the most and why? So till now, we were only looking at the photosynthesis part. We were kind of ignoring the relative humidity and carbon dioxide concentration. So humidity, here what they're saying is the humidity is reducing. So in that case, which plant is likely to reduce its stomatal conductance when the humidity reduces the most? So how can you do it? Let's consider the photosynthesis rate is the same. So at 50, when the photosynthetic rate is say 10 and the carbon dioxide concentration is not changing, only the relative humidity changes, then again this ball index is what is going to reduce or increase. So based on that, from what of the entity can you understand that the stomatal conductance is going to be affected the most? Yep, yep. So again, the red line. This is because you have to be careful that this value over here is actually, yeah, value over here is the Ball-Berry index and not just photosynthesis. So for the same value of photosynthesis, so for the same value of photosynthesis, say you're estimating 0.05 plus 0.05. What's this? Uh, if the AN value and CS value is not changing, and this is 5, and AN value and CS value is not changing, and this is 10, then this value is going to again be the one that is reducing. Not so we had learned about how the photosynthetic decrease will impact, but same thing will happen even when relative humidity is being impacted. So if relative humidity is going to reduce from this value to this value, what will be the change in the slope? Will be higher in this case as compared to this slope. So here this value is lesser than this value, which is nothing but again the slope of the equation. So from the slope, we can understand if it is sensitive to AN, if it is sensitive to relative humidity, and it is inversely proportional to carbon dioxide concentration. Now, for the same condition, if the environment is having a higher concentration of carbon dioxide, what will happen to the stomatal conductance? It, as the concentration of the carbon dioxide goes up, this Ballbury index will keep coming down. So again, the stomatal conductance will keep coming down. And that variation, this delta y by delta x variation is going to be the slope value. So from the slope value, the decrease will also be very high, increase also will be very high. So if the relative humidity is going to decrease, stomatal conductance is going to decrease very fast for the line with the highest slope. If the photosynthesis is going to decrease, stomatal conductance is going to decrease at a higher pace for the one with the higher slope. If carbon dioxide concentration is going to increase, stomatal conductance is going to decrease at a higher pace for the one with the higher slope. So higher slope is giving the relationship of the stomatal conductance to photosynthetic rate, to relative humidity, and giving an inverse relationship to the carbon dioxide concentration. So we can understand about the connection of stomatal conductance to the environmental variable and photosynthesis rates all through this Ballbury equation. Just by knowing what is the slope value of it. Intercept values again just giving the information of the minimal conductance when photosynthesis is zero. So this is what the uh, this Ballbury curve does. Now one more question. Where is it? Okay. Oops. So here I want you to estimate the stomatal conductance for all the three plants or all the three lines when the photosynthetic rate is going to be 15 micromoles per meter square per second. There is no change in the relative humidity or carbon dioxide concentration. Only the photosynthetic rate is changing. What will be the stomatal conductance values? What you need to find out. And what is it indicating about the water use strategy of each of the plant? Which one has the highest stomatal conductance? You can understand by this estimation. Correct. Ryan, your answer is right. Maybe also write a line about what is the water use strategy of this plant, which is represented by red line. Right. Correct. Any more answers? Have anyone else of you found the stomatal conductance? Line 3. What is the value of the stomatal conductance, Mayank? Okay, Ryan, I think this will be the end of the class since you've already answered and your answer is correct also. That will be the end for today's session. I think I'll wait for the others' answer and then end the session. Does anyone else have an answer or shall I move on? Okay, so yeah, the answer is here. So you just put, I said how 0.283. Okay. So this is how for the blue line, 0.07 plus 0.01 into 15, you get the answer as 0.22. Same for green line, you get 0.24, and for red line, you get it as 0.275. So here, the stomatal conductance is highest for the red line. This is because it is prioritizing high carbon dioxide uptake, but may lose more water through transpiration. So it does not just mean that I mean when photosynthesis is not happening, the stomatal baseline conductance is very low, but at the same time its sensitivity to photosynthesis is very high. So in such cases what we should understand is even the transpiration rate will be high because the stomata is going to the rate is going to be more and more. So we know that if the stomatal conductance to water vapor is 0.275, the transpiration rate is also increasing with respect to the carbon dioxide uptake uh, increasing. So, in terms of the water use efficiency, we cannot directly make an interpretation that this plant is highly water use efficient just because the baseline stomatal conductance is less. So, this connection also has to be taken because when the photosynthetic rate is increases, the rate of transpiration is also increasing with respect to this increasing photosynthetic rate. So it might not be very water use efficient plant. But again, if you see the baseline conductance is zero, so during conditions of very less carbon dioxide, that is nearing no photosynthesis, it is efficient in saving water during such times. So this will be the interpretation of this plant with respect to the water use uh, in in terms of water use efficiency. So these are all the stuffs that you can get from the simple line equation when we associate the stomatal conductance to this Baldbury index. And yeah, with this, I'll be ending today's class. Thank you for attending today's session. And we will meet again from Monday onwards. I think we'll be resuming our usual time of 6 to 7:30. If we yeah yeah, that's it. So we'll meet next on Monday. This will be the end of today's class. So bye bye. If anybody has any doubt, you can ask. I'll be here till 4:30. Otherwise, you're free to leave the session. Thank you.
Thank you, ma'am.
Thank you.